Uh, Good evening, everyone. Good evening, good morning, wherever you are. This is the first, lecture or webinar in the series of the statistical physics. This been recommended by Visitor Associate and Student Program Committee of the Essenbos Center. As you know, that Essenbos Center has a long history of organizing conferences, talks, seminars, and hosting visitors. And because of the pandemic, we were a little bit, interrupted on that front, and then we decided to have webinars, and we have two webinar series going on, one on quantum materials and devices and another on the statistical physics, and having a number of faculty members who are actively working in this field, it's apt to start such a webinar, and we are very happy to have Professor Mehran Kardar from MIT to give the first talk, and I request Professor S.S. Manna to introduce Professor Kardar. Thank you.
Okay, thank you, Arjun. So let us start. This is, I am Shubhranshu Manna, and I work in Essenbos Center for Basic Sciences. So it's a great pleasure to welcome Professor Mehran Kardar and of Massachusetts Institute of Technology. And so let me introduce him very briefly. Professor Mehran Kardar is the Francis Friedman Professor in the Physics Department at MIT, USA. His name is familiar to anyone working in the area of statistical physics. The two textbooks he has authored on the subject are used for most advanced courses on the subject. They are named as Statistical Physics of Particles and Statistical Physics of Fields. He is also well known worldwide for the Kardar-Parisi-Zhang equation, which he has named after him, which has been named after him and his collaborators. Professor Kardar's work has been recognized by a number of awards like the Bergman Memorial Research Award, A.P. Sloan Fellowship, Presidential Young Investor Award, Edgerton Award for Junior Faculty Achievements in MIT, and the Guggenheim Fellowship, to name a few. He is the fellow of the American Physical Society, the American Academy of Arts and Sciences, and the National Academy of Sciences. Today, Professor Kardar will be speaking on a topic whose title is Forces from Non-Equilibrium Fluctuations in Active Matter and QED. Now I request Professor Kardar to deliver his lecture.
Thank you very much for the invitation and the opportunity to talk in this forum. So I will start by talking about equilibrium fluctuations before going to non-equilibrium systems. And as a statistical physicist, I'm obligated to start with the ideal gas and the pressure of the ideal gas that is given by the standard formula of density times temperature, which is a very universal result because it does not depend on the properties of the particles. And as a manifestation of the fluctuations, it is even there when you are thinking about, say, the osmotic pressure of molecules in a solution, where the motion is very different from the particles of the gas, yet the change in entropy will give you exactly the pressure. Now, of course, when we become denser, when we are dealing with denser systems, the ideal gas law gets corrections that depends on the interactions of the particles. Now, I'm going to also talk about not only particles, but radiation, and I can convert the ideal gas law to the pressure of photons by just realizing that the density of photons is not something that is fixed, but changes as a function of temperature, inversely proportional to the volume that is occupied by the wavelength that is appropriate to photons of some particular temperature. So if we were to replace this volume with the volume that is occupied by one of these photons that grows like 1 over T cubed, we arrive at a pressure that is proportional to temperature to the fourth, which is the standard Stefan Boltzmann law. Now, this formula suggests that if we were to take the temperature all the way down to 0, the pressure would vanish. But that's not quite correct either, because as the temperature goes towards 0, this length scale that we defined diverges. And ultimately, when this length scale becomes of the order of the size of the container, let's say the separation between two walls, then we should replace this temperature scale with a scale that is appropriate to the distance between the walls. And so if we replace the temperature here with inverse of this distance, with the distance, what we arrive at is the Casimir force between two ideal mirrors, which is proportional to the inverse of the separation between the mirrors raised to the fourth power. So there is a connection between ideal gas law, the pressure of photons, the Casimir force that operates at short distances, and all of these can be related to fluctuations. In the case of the ideal gas, it's the thermal fluctuations. In the case of the Casimir force, it is the quantum fluctuations. And so what is nice about, say, this Casimir force is that it is, again, like the ideal gas, universal. It does not depend on any properties of the material, and it is just related to fundamental constants, h bar, c, and falling off with the separation to the fourth power. It's a force that is proportional to the area of the mirrors. And so if I divide force by area, again, I have a pressure. And just as an order of magnitude, once you reach distances that are a fraction of a micron, the pressure that you are dealing with will be of the order of some fraction of an atmospheric pressure. Since 1990s, this force has been experimentally observed in a large variety of experiments. And the thing is that in order to make this force measurable, one has to reach the distances that are of the order of micron and smaller. And indeed, when one goes beyond scales that are at scales that are smaller than a fraction of a micron, then the ideal nature of this Casimir force also changes, and it becomes dependent on the nature of the walls that are separating the two, and it kind of morphs at short distances the Casimir force to the van der Waals force, which does depend on characteristic material frequencies. And the nature of the power law changes from h bar c over d to the fourth to h bar times some characteristic frequency divided by d cubed. So again, all of these are things that are observed, and I just wanted to mention that there is this switchover between a very ideal form of the Casimir force that only depends on fundamental constants to at short distances becoming non-universal and depending on material parameters, much like when we are talking about the ideal gas. When we go to short distances, the ideality gets modified by properties of the atoms and molecules. So this was regarding the forces due to equilibrium fluctuations. Now I would like to go and think about examples where the fluctuations are out of equilibrium. And the subject that has attracted much attention in the past decade is topic of active matter. So active matter could refer to live matter, such as bacteria that are moving around and maybe hitting the walls of a container, or artificial active matter, which are these colloidal particles that are asymmetrically coated, so that when light shines on them, there is a difference between the force that is experienced on the two sides of the colloidal ball, and they start to move. And if we switch off the light, they stop. And if the light is switched on again, then they would start to move. So this is activity of these particles is externally controlled. And there are other examples of it, like if we put lots of grains on a surface and start shaking them, we get situations where the particles collide with each other and collide with the walls of the container. And so artificially, we look at these systems from far away, and they're kind of collection of particles that are moving around, hitting each other. And maybe we can think of them as being similar to the particles of the gas that are moving around and hitting walls of the container. And should we regard the system of active particles that are moving around as somehow being equivalent to some kind of a gas and associate with them something like a pressure that they are exerting on the walls of the container? Well, this is a question that we asked 5 or 6 years ago with a group of colleagues that are listed over here. And in order to address this question, we wanted to have a very simple model of active matter in which we could do calculations and maybe do simulations. And the standard model for simulating active matters is essentially two varieties. One of them are called run and tumble particles, which, like bacteria, you have particles that are moving along trajectories. At some point, they decide to change direction and go somewhere else. And so they execute a kind of random walk that is composed of segments that are straight and then turn around. Or one could smoothen out these changes in angle and have what is called an active Brownian particle in which the orientation is smoothly changing as a function of position along the trajectory. So the equations of motion that would describe these is that a particle's velocity moves along some particular direction with a given uh, uh, speed, and then there are fluctuations that are kind of like what you would have for the Brownian particle, but importantly, the orientation with which this speed is assigned changes as a function of time in some random manner. The random manner can either be continuous or it can be this run and tumble type of form. So the only difference between this equation, this set of equations, and very standard Brownian particles that we have been used to since the time of Langevin equation and Einstein's description of Brownian particles is the existence of this velocity v. So if I set this velocity v to this speed v to 0, then it's just a standard description of Brownian particles. So the question is, how does the presence of this speed v, which in some sense breaks time reversal symmetry at the microscopic level, modify the description of the system at the macroscopic level? So basically, we had a collection of these particles that were moving in a box. And in order to calculate forces that are exerted on the walls of the container, we had to impose a potential that was describing the wall of the container and indicated in red here. It's a potential that diverges on approaching the wall, so that the particles, when they approach the wall, feel a force that pushes them back inside. Now, if we were dealing with a system of particles in equilibrium, these set of conditions would give rise to a variation of density. The density would go down in the vicinity of the wall. And then using that density and the force that is exerted on the wall, we could calculate a force or a pressure. And for systems that are in equilibrium, the density is related to the potential through the Boltzmann weight. Then force being the derivative of the potential, it is very easy to integrate this equation and get the standard ideal gas law, which is the density times kT. And so that shows that the form of the pressure that is exerted on the wall is completely independent of the type of potential that I impose on the wall. And the universality of the ideal gas, this is a reflection of that. No matter what potential I use, if I go through this calculation, I will get the ideal gas law. But what is the density when we are dealing with an active system? Is it the same type of density that we had for the Boltzmann weight or not? And so we calculated this density, but we had to add one more element because we are dealing with particles that are moving with a particular speed along some particular orientation. We had to specify how the orientation was changing in the vicinity of the wall. And naturally, we assume that there is some kind of a torque so that when the particle that is like a bacterium approaches the wall, the front and the back of the bacterium will experience different forces from the wall that causes a rotation and there is a torque. When we included the effect of this fact, this observation into the calculation that I had outlined for you before for the ideal particle, we got a different result. The form for the pressure has a part that looks like the ideal gas result, but because of the pressure that is experienced by the particles, there is another contribution that explicitly depends on the form of the wall potential. So that is kind of surprising because it says that you put the particles that look very much like a gas of ideal particles in a box, but depending on whether the walls of the box are made of wood or glass or something else, the pressure that is exerted on the wall is different. So the consequence of that is indicated in this movie, where in the movie the particles that are on the right and the left box start with exactly the same initial density, but the walls of the container on the left and the right are different. And although the densities are the same, the pressure that is exerted on the piston that is movable in the middle is different, and it spontaneously starts to move in one direction. So it is like having, say, the gas in the room that we have over here, and we put a partition that is glass on one side and wood on the other side, and the partition spontaneously moves in one direction or the other, something that we don't have for the equilibrium matter, but occurs for these as a consequence of these non-equilibrium fluctuations. Yet another thing that we could do, for example, is to confine these particles in a box and then, well, actually imagine that you have bacteria that are moving on a plate, and you put a box on top of these bacteria where the box is like a rectangle, but the two sides of the rectangle are different, and then the entire box will start to move in one direction or the other. So that's an interesting observation that depends on the nature of the wall, but the actual shape of the wall has also consequences. So if we imagine that the confining wall, rather than being flat, is something that has some sinusoidal modulation, it turns out that the accumulation of the particles on the hill as opposed to the bottom of the hill is very different. And because of the difference in accumulation of active particles, depending on where the curvature of the surface is, there are differences in pressure between the top of the hill and bottom of the trough. And not surprisingly, because that's the only geometric object that remains, the variations in pressure are related to the radius of curvature. And again, we could sort of confirm that indeed the variations in pressure as a function of the radius have this linear relation, which is kind of reminiscent of something that is known as Laplace's law, that if you have a curved object, the changes in pressure across the curvature are inversely related to the surface tension divided by the local radius of curvature. So these observations that we have, we can relate to a change in a surface tension or line tension that is numerically we find to be proportional to the pressure and what is called the run length. And the run length is the typical distance that these particles move before they change direction. There is a kind of persistence length to these random walks that is an interesting and important property of these particles and determines what the modification in the line tension is. Interestingly, what we find for our system is that the modification in line tension is a negative contribution to the line tension. So it tends to make the system unstable. And so if this contribution to the line tension due to curvature is sufficiently large, then the line or the boundary wants to become spontaneously curved. And this is indeed something that is seen when you put a chain in a solution of these active particles, then it spontaneously tries to make its length as large as possible because of this negative line tension that you have imposed on the system. And another consequence of this is that if you put a flexible worm inside the solution of these active bacteria, if it spontaneously changes curvature, then the pressure that it feels on the left and on the inside and the outside are different. And because of the differences in pressure, it starts to move in some particular direction. So I kind of like to think about this as having a sailboat where there is no wind, but when the sail curves, it spontaneously generates the wind that pushes it around. And this, for this particular worm, the characteristic persistence length is of the order of the size of the worm. If the worm is much larger, then it executes this curious motion that essentially indicates the various instabilities that there are in the system. So the story here is that the fluctuations that one sees for these active particles exert non-trivial forces on the boundaries of the system of active particles. Now, one other consequence of these active fluctuations is that you can create tangential forces. Now, in equilibrium, it does not happen. So imagine that we have a ratchet shape, and it is subject to these fluctuating systems that are impinging on this. And you would say that because of the asymmetry of the system, maybe there is more force that it goes in one direction as opposed to the other direction, and this system should move either or feel a force either to the right or to the left. Now, in equilibrium, that cannot be the case, because the idea of equilibrium is that if I were to run the movie forward or backward, you wouldn't be able to tell the difference. So if the system is in equilibrium and I say that there is a force that is trying to move me to the left, then I would show the same movie and I would say, running it backward, there should be a force that is going to the right. So the time reversal symmetry that we have in equilibrium says that you cannot convert equilibrium fluctuations to a tangential force that is either pointing to the right or to the left. But when we go out of equilibrium, such as in the case of these bacteria, that's no longer the case. And indeed, one can show both numerically and with this very nice experiment that if you have a ratchet and a collection of bacteria that are not out of equilibrium, so this gas that is on the outside still is fluctuating, but in non-equilibrium fashion, you can convert the fluctuations into a force from which you can extract work. So the question that we would like to pose is now, in what circumstances can we convert these non-equilibrium fluctuations in a means of extracting work? Now, Feynman, when he describes this particular system of Ratchet and Paul, actually says that if there is a temperature difference between the two boxes, you can cause this ratchet to spontaneously move in some particular direction and use the resulting force to maybe lift a mass and have a kind of heat engine that takes advantage of the difference in temperature and causes work to be done. So we would like to kind of build upon that idea of Feynman and have a heat engine that takes advantage of these kinds of ratchet forces and creates some kind of useful work. So the first element that we need is objects that are at different temperature and there is a transfer of heat. So this again looks like something that is very classical and related to what I had told you at the beginning, that essentially associated with objects at a particular temperature, there is a pressure that is proportional to temperature to the fourth power. Associated with that, there is also a heat transfer between the two bodies, which is the difference of the heats raised to the fourth power. This is the standard Stefan Boltzmann law that we teach in undergraduate physics. But it turns out that this nice result is only valid when we are looking at very large distances. And when we bring the two systems close to each other, the transfer of heat from the hot to the cold is not simply proportional to the fourth power difference, because this is a formula that you would say is independent of how far these two plates are to each other. But when you go and do the actual experiment, which was done, let's say, in 2009 by a colleague at MIT, you find that when you bring this heated sphere close to a cold surface and you measure how much heat has been transferred as a function of separation, it is not a constant as a function of separation. So actually this black line here over here does not go to zero, but it goes to a finite value, which is the prediction of this Stefan Boltzmann law. And the experiment shows that when you reach fractions of a micron, the amount of heat that is transferred from the hot to the cold increases by orders of magnitude. In fact, it appears to diverge at very short distances. And the reason for that roughly is the following, that the Stefan Boltzmann law describes the transfer by propagating photons. But when the two particles, when the two objects are very close to each other, the main source of heat transfer is not propagating modes, but the tunneling of heat from one to the object through evanescent modes. And so the question is, how does one describe things beyond the standard propagating modes? And the way to do so is a very nice formalism that was developed middle of last century by Ritov. And he gave it the very nice name of fluctuational quantum electrodynamics. The idea is, let's imagine that we have a bunch of objects here with different colors, and each one of them is held at a different temperature. So because we are going to try to describe non-equilibrium phenomena. how can I describe the forces and the heat transfer between these objects? What Ritov said is, when I say that I have an object that is at a particular temperature, it means that there are fluctuations in that object that are characterized by that temperature. And when we are talking about the electromagnetic field, there are going to be currents that are fluctuating in each one of my objects. The average of the current is 0, but the fluctuations of the current is related to temperature as well as quantum fluctuations by the standard Bose formula. Now, if I have fluctuating currents, then it's a classical result that the current creates an electric field. And so in principle, if I know an instantaneous current in the system, I can use a Green's function, which is hard to calculate for different an arbitrary set of shapes. But in principle, there exists a Green's function that relates the instantaneous currents to the instantaneous electromagnetic field. Since the current is on average 0, the electromagnetic field is on average 0. But the fluctuations in current can be translated to fluctuations in the electromagnetic field, whose averages I can compute at any point in space if I know what the Green's function is, and if I know what the temperatures are of the objects, because I can then calculate the current fluctuations. So what Ritov said is that if you know the temperatures of the objects and the properties of these objects, because the nature of the current fluctuations through the fluctuation dissipation theorem is related to the imaginary part of the dielectric function that describes each of these objects. But once you know that all of those properties, you can in principle calculate the fluctuations of the electromagnetic field, and from various quadratic forms, you can calculate, for example, the Poynting vector and calculate the heat flux, or you can calculate the stress energy tensor and hence calculate the forces that are acting on the objects. And so if you use this formula, you can explain the various results that one obtains. For example, one can show that this divergence that one has at short distances can be related to some characteristic resonance frequencies of the objects, and the heat transfer should diverge at short distances in that, according to that. One can sort of calculate forces. For example, here we are sort of looking at the force that is exerted on a hot tungsten plate as it is approaching a cold surface. Because of the non-equilibrium force of radiation, there is something that tries to levitate this particle, but if we allow it to also radiate away, it cools down and eventually falls down. Now, there is on average a force on each of these objects, and there's heat that is leaving upon these objects. You would say that if I go to equilibrium where all of the temperatures are the same, then there should be no heat transfer. Well, that is true, but only on average, because everything that we are measuring is because of fluctuations. Things like heat flux, forces, etc., even in equilibrium, they have fluctuations. And since I know everything about this system through the Ritov formula, I can calculate not only the mean value of the forces, but also the fluctuations of the forces, fluctuations of the heat transfer, and correlations between the heat transfer and the force at different times, even in equilibrium. And even in equilibrium, these quantities, while the averages are 0, the fluctuations will be non-zero. But then there are very nice results in thermodynamics that relate equilibrium fluctuations to response functions. So for example, if I know the force-force correlations, I can convert that to a change of the mean force with velocity, which is a friction coefficient. If I know in equilibrium the heat fluctuations, I can convert that to a change of heat with temperature, which is the heat transfer coefficient. And the cross correlations have this symmetry. It doesn't matter if I correlate heat with force or force with heat, but they will give me two different response coefficients that will have to be related to each other through what's called the Onsager relations. So these formulas will be useful to me when I finally decide to construct my engine. So let's go back to the idea that I have a ratchet and I heat up the ratchet and there should be some kind of a force that is acting on that. When I go and use these formula, I find that the heat transfer and the force that is exerted to this have some complicated forms that depend on scattering of object from these ratchets, which is hard to calculate. But the thing that is nice is that there is some usual occupation factor for a particular frequency at a temperature, and the amount of heat that is leaving the object is proportional to the frequency h bar omega, this occupation, and then something complicated that is dependent on the nature of the ratchet. And I can calculate the force that is acting on the ratchet, and it has a very similar formula, except that h bar omega is replaced with h bar k, which kind of gives you the impression that what is happening is that this object is releasing photons, and these photons are carrying energy h bar omega and carrying momentum h bar k, and because of this, there is a force. So I need to preferentially emit photons in some particular direction, right versus left, in order to get a net force. There is, however, even without calculation, you would say a big constraint, because the omega and k are related by omega equals to ck, the standard relation between frequency and wave number. And since this involves the speed of light, which is a very, very large number, you would say that the scale of the force that I would get would be smaller than the scale of the heat that I transfer by the order of the speed of light. It turns out that there are some other conditions that constrain this. Like, for example, we could not really calculate the results for an arbitrary shaped ratchet. So we said, okay, let's try to imagine a flat surface, but the material that comes to the end of that flat surface has a right-left asymmetry. When we calculated for this material what with a flat surface, what the nature of these scatterings are, we found that the net force was 0. And there are some theorems that were described by Shanhui Fen that describe why that is. And we need to find a different form of breaking the symmetry that is in this problem that is also called reciprocity. And we found that a very nice way of doing so is to have flat surfaces, but exert a magnetic field that is orthogonal to this system and comes, let's say, parallel to the plates. And this magnetic field breaks the symmetry of the system between right and left in a fashion that there is indeed, if there is a magnetic field, there is a force. And so in principle, you could generate a cylinder with a magnetic field along its axis. And if you have such a system, there will be a force that will try to rotate the axle compared to the boundary. So you would have a means in principle of having heat that is transferred between these two objects, and along with the heat that is transferred, there is a force that tries to move the two surfaces relative to each other. Fortunately, also, the problem that we described, where the nature of the force had to be smaller than the heat due to the speed of light, which was a large number, can also be modified if we go to very short distances for the same reason that the heat transfer was diverging at short distances. The force also diverges, but even diverges more rapidly than the heat transfer, such that when we get to distances that are in what is called the near field regime, when you are at scales that is shorter than the characteristic frequency divided by the speed of light, the magnitude of the force is no longer constrained by this, but as indicated by this orange line, can exceed this condition that we have over here. So in principle, by going to distances that are sub-micron, we can make the ratio between force and heat transfer arbitrarily large. So let's go and look at that near field regime. So we have two objects that are at a distance d from each other that is very small. The heat transfer will diverge as d goes to 0, and the amount of heat that is transferred is naturally proportional to the temperature difference when the temperature difference is small, is related to this natural frequency and diverges. But as I said, the force actually diverges even more rapidly as 1 over d cubed. Now, of course, there is a parameter that describes the degree of asymmetry, which if we put the magnetic field on, is related to the ratio of the cyclotron frequency that is associated with the magnetic field to this natural frequency. And so that is giving me the scale of the force that from which I want to extract the work by moving these plates with respect to each other. Now, it is important to realize that in order to extract work out of the force, I have to move the plates with respect to each other because the power that is generated is proportional to the product of the force and the velocity. So if the velocity is 0, there is a force, but there is nothing that is extracted. In order to get useful, I have to move the plate. So the velocity times force is the power that I extract, and I can define an efficiency, which is the ratio of the product of the work times force times velocity, which is work divided by the heat. And if I look at that formula, you would say, well, why can't you make this V arbitrarily large and hence get an efficiency that is very large? And indeed, you would say you could get to the Carnot efficiency, which is of the order of the difference in temperature divided by temperature, provided you choose a speed here that is of the order of this ratio of h over fy multiplied by the Carnot efficiency. So is there anything that prevents the system to have very high efficiency? Well, the thing is that we calculated all of these results, the heat transfer and the force, assuming that the two surfaces were not moving with respect to each other. And as soon as the two surfaces move with respect to each other, these formulas have to be modified. And the various relationships that I gave you before, the Onsager relation, for example, tells you how this modification should occur. So what Onsager relation tells you is that if for 0 velocity you know what the heat transfer is, if you increase the velocity, the heat transfer will also change by an amount that is related to the way that the force depends on temperature differences. This is the Onsager reciprocity condition, which means that in order to move at some velocity v, you need actually to have more heat that is extracted from the object. That's not the only relation. The other relation is that the force that is experienced is reduced if I start to move because there's also a friction force. And the friction force is again something that we can calculate through these relations that I had showed you before through the Rito formalism. The outcome of the story is that if you calculate the eventual efficiency as a function of speed, it is reduced from the Carnot efficiency by various relations. And one can see that at zero velocity, of course, you don't extract any work and the efficiency is zero. As you go to large velocity, ultimately these corrections will make the efficiency go to zero again. So there is a velocity at which you can extract the maximum power from this engine, and you can relate that max velocity at maximum power to various material properties and calculate what the optimal efficiency is going to be at maximum power. And it is going to be reduced from the Carnot efficiency by the efficiency with which your engine converts the heat transfer to force. Let's see, I have 5 minutes, so let me just mention a couple of other interesting things. So what I described before was that if you have two objects that are at different temperatures and there is nothing between them, just vacuum that is at some temperature, and you start to try to move one of these objects with respect to the other, there is some frictional force. And that frictional force, I guess I had it over here. Oops. That frictional force through the coefficients that you have over here is proportional to temperature. And you would say that at zero temperature, the force has to go to zero. And the reason that's correct is that if you imagine that you are thinking about two surfaces that are in vacuum, and you move one with respect to other at some velocity v, because of relativity, it shouldn't matter what the velocity is. And because of the constraints of special relativity, you would say that the force, there should be no frictional force in the sense that the force should not depend on velocity. And that is correct. But what turns out is that there is still dissipation, but the dissipation is not proportional to the rate of change of motion, but the third derivative of motion as a function of time. This was a result that was obtained by Moore, Fulling, and Davis back in the 70s, that essentially if you have an object that tries to move in vacuum, by itself it has, I mean, you can move it in any frame with different speeds, so those things should not have any difference with each other, so the force cannot be proportional to velocity. But as soon as the object starts to accelerate so that there is a third derivative of motion, there is a dissipative force that opposes its motion in vacuum. And if there is a dissipative force, there must also be some energy that is leaving the particle, and that is in the form of radiation that goes into the vacuum. So if we try to write down an equation of motion for a particle at zero temperature in vacuum, we would say that there is mass times acceleration, and then there is a frictional force, but the frictional force is not proportional to the derivative, but through the third derivative with respect to time, which in frequency domain becomes the I omega cubed. So if there is no force that is acting on this particle, then that would be the equation of motion with the right-hand side to zero. But in the same sense that if we have a particle that is in a fluid, it experiences the forces of fluctuations from the particles of the fluid. If we have a metallic sphere, let's say, that is sitting in vacuum, it will experience the fluctuations of the electromagnetic field that have to be in vacuum even at zero temperature, the quantum fluctuations. So there is a fluctuating force, and if the particle was charged, the fluctuating force would be its charge times the electric field, which is the gradient of some potential. But if the particle has zero charge but is polarizable, the force that it will experience will be proportional to the square of the electromagnetic field fluctuations. So we have an interesting situation that is kind of analogous to a Brownian particle, except that rather than the friction being proportional to velocity, it's proportional to the third derivative velocity, and the fluctuating force that it experiences is the square of the gradient of something that is due to quantum fluctuations. So for that system, we calculated the analog of the displacements of the particle as a function of time. And as a function of time, it fluctuates, but the extent of fluctuations is much less than diffusion, and one can show that it is proportional to logarithm of time. But more interestingly, if one looks at the probability distribution of how far the particle has moved as a function of time, it is no longer a Gaussian with this variance, but it is something that is like a power law distribution. It's a Levy flight. So the particle that is polarizable, you put it in vacuum at zero temperature, it kind of disperses in this unusual fashion. I think I'll skip the next thing that I had because of the lack of time and go immediately to the summary. So basically, we started with the idea that if you have a system that is fluctuating, those fluctuations, if they are reduced because of the existence of some boundary, will exert forces on the boundary. And of course, the natural example of that is the fluctuations of particles in a gas. And if we confine the extent of those fluctuations, we get the ideal gas result for the pressure. And we can connect those fluctuations ultimately to quantum fluctuations. And the quantum fluctuations, if they confine between two boundaries, will give you the Casimir force. And the nice thing about both of these results is that they are universal, independent of properties of the particles or the confining walls. But when we go to non-equilibrium fluctuations, the situation changes. And we have this result that even the idea of pressure has to be reinterpreted in the sense that it depends on the interaction of the particles with the confining walls. And the pressure is not only a function of density, but it's a function of density depending on the nature of the confining walls. And that there are also not only material dependencies, but also shape dependencies, so that the pressure on a curved object depends on the curvature in a manner that can create these spontaneously moving objects. And so then we ask the question of whether it is possible to convert these fluctuations out of equilibrium in order to extract work from the system. And in particular, we wanted to construct an engine that was based on non-equilibrium fluctuations due to a current of heat that was going from one temperature to another temperature. And to calculate this, we had to employ this Rito formalism that converts the fluctuations that have thermal and quantum origin for the currents within each body to the electromagnetic field outside the bodies, whose statistics will enable us to calculate both the heat transfer, the force, as well as quantities such as the coefficient of friction, coefficient of thermal transport, etc., which we would need in order to quantify what happens when we have an engine. And we found that we could indeed, using a magnetic field, construct an engine that operates on the basis of converting the heat transfer between two objects into a force that moves this engine around, and we could calculate some limitations on the efficiency of this engine. And whereas all of these reductions in efficiencies were due to friction forces, etc., where one is looking at the effect of friction at finite temperature, there are also interesting things when we go to zero temperature, and these dynamic Casimir phenomena are a number of things, one of which was this anomalous flight of a classical particle in a quantum bath I described for you. So the work that I mentioned has been a culmination of a lot of collaborations. The work that had to do with active matter was with Alex Solon, Yarif Kafri, and some senior collaborators, including Aparna Bhaskara, Michael Cates, Julian Tayor. The work on Casimir physics has involved a number of students and postdocs and faculty at MIT. The most recent aspect of this work, which was the engine, was done with David Gelbwasser, Noah Graham, and Matthew Kruger. And I thank you for your attention.
Thank you, Professor Kardar, for the wonderful talk. So now it's time for some questions, maybe? Shakuntala, go ahead.
Yeah. So I have a question. You had mentioned that these flexible objects in this active medium. Okay. Now you had mentioned that they undergo shape fluctuations. Now I was thinking that suppose if I measure some quantity, if I would like to characterize this fluctuation, suppose I measure some quantity like local height gradient and
yes.
what do I expect about, let's say, its distribution? Of course, as it's undergoing its shape fluctuations, the local height gradient at any particular point will change with time. It will fluctuate. What kind of distribution I expect in this case?
That's a very good question. I would say that at least, let's say, for this very complicated object that I have on the right, maybe rather than thinking about height fluctuation that I would have to calculate with respect to a base plane, I could look at each location and its curvature. And I could ask, how does the curvature fluctuate as a function of time and as a function of, say, distance along the length of the worm? And that will have two aspects. One of them is the fluctuations of the force that is coming from the medium. And we know that it is on average is related to curvature through these formulas. But how that quantity changes as a function of time, what is the correlation between the force that is exerted at some instant of time and another instant of time, which you can then try to convert to the dynamics of these fluctuations. Actually, I don't think we know that. So maybe I would translate your question to the question of, I have given you results in this case for what is the average force and how that average force depends on pressure. But what are the fluctuations of that, and how are the fluctuations of that force varying as a function of time? And I don't know the answers to that. So those are sort of basic things that I would need in order to start building the formalism that will eventually give the answer to the question that you asked. So that's certainly a nice project to pursue.
So suppose if I had multiple such objects, then I was wondering if I could also treat them, those objects, as another active medium.
Yes. So what you are saying is, so here I said that I have one passive worm, and I put the passive worm in this bat, and it started to move in some direction, so it became an active object. And what you're saying is, what if I have multiple of these active objects? Now, one thing that we have calculated and is interesting is that if you have multiple of these objects, actually, let's say 2 of these objects, they actually have a long-range force between them, because the presence of one of them modifies an average current of active particles, which then extends over the size of the medium. It's kind of like having a fluid, and you disturb the fluid at some location. You set up a Green's function for how the velocity is changing across the fluid that falls off as a power law. That also holds for this active medium. So the issue when we already have 2 objects is that one of them exerts forces on the other one over large distances. So if I have multiple of them, it's actually a rather complicated, more complicated than what I started with, because I would then have not only a collection of these active particles, but these active particles would have long-range interactions between them. So I don't say that it is not a doable object, but it is at least one level more complicated than the one that we currently have.
Yes. Okay, thank you.
Okay, Punabrata?
Hi, can you hear me?
Yes, I can hear you.
Yes, yes.
Yeah, so I have a question regarding that calculation of pressure in active gases and ideal gases.
Yes.
And you calculated pressure as the average of del V del X, right?
We calculated.
Yeah.
This is the formula that you are asking about?
No. Yeah. This is the gradient of wall force. So
Yes.
okay. So this is, I mean, pressure could have been calculated in different ways, like calculating the momentum transfer. Say, I mean, literally calculating that how many particles are hitting the wall and changing their direction, and momentum is being transferred to the wall. So that I would probably call kinematic pressure or something. And ideal gas case, they must be same in equilibrium.
Yes. Yes.
But in active gas, it is not absolutely clear. I mean, how do you calculate pressure from kinematic consideration? Because it's a momentum non-conserving system. So could you clarify, or does that question make sense?
Exactly. So I think this is maybe a very interesting result that you're pointing out, which is that if I'm calculating the pressure of the gas, I can use it through the standard derivative of the log of the partition function. And when I'm calculating the partition function, I integrate over various things. And the effect of momentum does not contribute to this formula, because it's just the volume to the power of n.
Right.
So the result for the ideal gas, I can completely ignore what the dynamic effect of the change in momentum is. And I would get the same result not only for particles that are ballistically impinging on the container and exert momentum, but also for solute particles which are kind of moving in a dissipative medium, and I would get the same result. Now, it is interesting that for the ballistic particles, you can do the dynamical calculation and get exactly the same ideal gas pressure as here.
Yes.
Actually, I don't know how to do that calculation for the dynamical perspective for solute, like salt molecules in water, where I would calculate the osmotic pressure. So I would say that the calculation that I need to do for the active particles is more like the calculation that I would do for solute particles and getting the osmotic pressure in a solvent, as opposed to uh, 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 the ballistic formula that you have. So I guess the short answer to your question is that I know how to do the calculation in this fashion,
Yes.
but as you say, these equations of motion are not conserving a momentum. So the only way that I know of relating force through the equations of motion is by relying on the gradient of V. And that's what we've done over here. So from the perspective of these equations, it is consistent, but I would like to see the answer to your question expressed in the way of how would you calculate the osmotic pressure of molecules in a solvent, and try to see whether that kind of calculation we
Yes.
could extend to this system. And we haven't done that, and I don't know in a straightforward manner how to do it.
Okay. But I mean, maybe, I mean, is it possible to set up? That's another thing. I mean, I don't know. I mean, how do you set up the thing in a kinematic ground? Is it at all possible? You think yes?
I haven't thought about it in that
Okay.
fashion, so I don't know. So all I can say is that through these equations, we have a dynamical formalism, but it's a dynamical formalism that relies on dissipative equations of motion.
Yes, I mean, also, I mean, using this formula, I mean, just translating from equilibrium to active gas, it's a bit of arbitrary thing. I mean, you don't.
No, if I set V equals to 0 in this equation, I go to equilibrium.
Yeah, that is correct. I mean, of course, it has to be.
Right.
But I mean, for example, it does not say anything about, say, phase equilibria. I mean, it does not say anything about density fluctuation or say volume fluctuation, or does it say anything about volume fluctuation?
Well, I can convert these equations to equations that describe density fluctuations, right? So you can, I mean, there is certainly this Dean-Kawasaki formalism that takes these Langevin equations, including the velocity, and converts it to an equation that describes the density. So that formalism exists, and people have done that.
Okay, but is that related to this pressure? Or I mean,
yes. So this result you could alternatively get from that formalism, but yeah, I don't think it adds anything to what I have said here.
Yeah. Okay, thank you.
Rajarshi?
Yeah, so my question is on your flexible chain in active bath. So
yes,
if you make it more rigid, say if you make it rod-like, so do you see a rotation,
right,
like instead of this motion? What happens as a function of bending rigidity if I make it more rigid?
Okay, so this is the left one is the thing that is more in the rigid limit. And so really the only mode that you are seeing is kind of like a bending of a rigid rod.
Yes.
Right. And it seems to have a net velocity in some direction, but there does not seem, at least for this simulation, to be a average torque in one direction or the other. So I think one needs to break some other symmetry, which at least for this system, I don't see how to do that. So you want essentially the top and the bottom portion of this rod to
You can make
experience
it,
different forces.
yeah. You can make it chemically asymmetric. Maybe you can make half
Yes.
of the rod, say, sticky to these particles, and then maybe there will be some
Right.
resultant
So
torque in that case.
I agree. If I think you make the top and bottom of this rod to be different, then there should be a torque. Yes.
Thank you.
We haven't done that.
Okay, there's one more question in the chat box. So Chandradeep, if you want, you can directly ask.
I have a naive question that if that fluctuating chain, we form it as a kind of loop, then the shape fluctuation, will it be qualitatively different than the present case where it is have two free ends?
Okay, that's again a very good question. So what happens if this object, rather than being a rod, is a circle? Now, the thing that I have to worry about if I'm living in 2 dimensions is whether the particles that are on the inside of the loop can go to the outside of the loop. If they can go from the inside to the outside, then we don't have these phenomena. If they are always confined to the inside of the loop, then you have an additional constraint that we haven't implemented. So the nice question to ask, or some qualitative question, is suppose that I have start with a circular shape for this loop on average, and then I have some active particles on the inside. Would it spontaneously change its shape from a circle to something like an ellipsoid? In some sense, maybe it is related to the question that was asked before, whether there's also going to be a net rotation of this object with a torque. And I would imagine that for the very simplest cases of particles and symmetries that we have, the shape of this object will remain more or less as a circular loop that is fluctuating a little bit. But yeah, but that again is that's my guess. One can try to simulate that, but then as I said, the most important thing is the constraint that the number of particles that are on the inside does not change. I guess you can also ask the situation, if you have a loop in 3 dimensions, what does it do when you don't have that constraint? And again, I don't know the answer. So there's certainly lots of good questions here.
But would it start moving even if it doesn't change the shape much? So if there are active particles.
So let's stick to 2 dimensions. So you're saying let's
yes.
make this rod into a circle in 2 dimensions. Then I would say that as long as you're dealing with a shape that is on average circular, then which direction should it move? There is no asymmetry. So in order for it to start to move in some direction, I have to impose some kind of asymmetry, like the asymmetry of the sail that takes place in this case. So the question is whether the loop will spontaneously go from a circle to something that is shaped like a lens. And my feeling is that if it does change its shape to something that is like a deformed lens, then it will move, but it may be such a rare fluctuations for it if there's particles that are confined on the inside that they would oppose that shape.
Okay. But there were some experiments where they had some real bugs, like live bugs, within a some sort of a circular shape, but stiff boundary, and then the bugs were smaller in number, like 5, 6, or maybe 10, and they actually started to push the whole thing, and it started to move. Is it's some sort of a number effect? It's just in one trajectory it moves in one direction, and in another it would move in some other direction. On an average it would not move, or so this symmetry breaking, was it just a small number effect somehow?
No, I think you can do that, but you may indeed have to have rules that are different potentially from the rules of our particles. So I guess what you're saying is that somehow you have the particles within this shape, and once it started to move in some direction, there must have been some positive feedback effect that made more particles go in that direction. So I can certainly imagine constructing a system that has that kind of positive feedback, but probably not in the system that we have. Yeah, so that certainly just points to another question, that the universe of non-equilibrium fluctuations is much wider than the ones that I have told you here and beyond what we've explored.
Okay. Yeah, one last question. So at the very last slide, you showed this quantum Brownian motion, where the mean square displacement is growing as log t, but the distribution looked like stationary. Yeah, here. Is it true? So it is stationary within this regime, is it?
Yes. So basically, this quantity, so imagine that you have a Brownian particle in the usual sense that we know. Then the Brownian particle, as a function of time, will spread, and the shape of the spread is a Gaussian whose variance will grow with time.
Yes.
Now the shape of this object is this Levy distribution, where the parameter, the width of this that is related to this quantity x0 also moves in a way that the typical variance is growing logarithmically.
Okay. So x0 depends on time. Okay. So
yes.
Okay. Okay. Thank you. Are there any other questions? Yeah, if not, let's thank Professor Kardar once more for the wonderful talk and also giving it at such an unusual hour. Thank you very much.
My pleasure. Thank you.
Thank you. Bye.